understand why we need a special method to do this, let's repeat what we did earlier, but with different values of k. Let's set them to these values. The following code uses the function mapdf to apply the same model, the same code for each one of these k's. You could do it like this. Note that we estimate accuracy by using both the training set and the test set. And now we can plot the accuracy estimates for each value of k, both for the test set and the training set. Note that the estimate obtained with the test set is generally lower than the estimate obtained with the training set as expected, but the difference is larger for smaller values of k. This is due to overtraining. Also note that the accuracy versus k plot is quite jagged. We do not expect this to be jagged because small changes in k should not affect the algorithm's performance too much. The jaggedness is explained by the fact that the accuracy is computed on a sample and therefore it's a random variable. This demonstrates why we prefer to minimize the expected loss rather than the loss we observe with just one dataset. If we were to use these estimates to pick the k that maximizes accuracy, we will use the estimate built on the test data. So the k that maximizes accuracy is 41, and this gives us an accuracy of 86%. Another reason we need a better estimate of accuracy is that if we use the test set to pick k, we should not expect the accompanying accuracy estimate to extrapolate to the real world. This is because even here we broke the golden rule of machine learning. We selected the k using the test set. Cross-validation also provides an estimate that takes this into account. We previously explained that a common goal of machine learning is to find an algorithm that produces predictors y hat for an outcome y that minimizes the mean squared error. When all we have at our disposal is one dataset, we can estimate the MSE with the observed MSE with this formula. The theoretical MSE and the observed MSE are often referred to as the true error and apparent error respectively. Now, there are two important characteristics of the apparent error we should always keep in mind. First, because our data are random, the apparent error is a random variable. For example, the dataset we have may be a random sample from a larger population. An algorithm may have a lower apparent error than another algorithm due just to luck. Second, if we train an algorithm on the same dataset that we use to compute the apparent error, we might be overtraining. In general, when we do this, the apparent error will be an underestimate of the true error. We will see an extreme example of this with k nearest neighbors. Cross-validation is a technique that permits us to alleviate both these problems. To understand cross-validation, it helps to think of the true error, a theoretical quantity, as the average of many apparent errors obtained by applying the algorithm to b, a very large number, new random samples of the data, none of them used to train the algorithm. In this scenario, we think of the true error as the following formula, with b a large number that can be thought of as practically infinite. As already mentioned, this is a theoretical quantity because we only have available one set of outcomes. Cross-validation is based on the idea of imitating the theoretical setup we just showed as best we can with the data we have. To do this, we have to generate a series of different random samples. There are several approaches we can use, but the general idea for all of them is to randomly generate smaller data sets that are not used for training and instead used to estimate the true error. The first version of cross-validation we describe is k-fold cross-validation. Generally speaking, a machine learning challenge starts with a dataset. We need to build an algorithm using this dataset that will eventually be used in completely independent datasets. But we don't get to see these independent datasets. So, to imitate this situation, we carve out a piece of our dataset and pretend it is an independent dataset. We divide the dataset into a training set and a test set. We will train our algorithm exclusively on the training set and use the test set only for evaluation purposes. We usually try to select a small piece of the data set so that we have as much data as possible to train. However, we also want the test set to be large enough so that we obtain a stable estimate of the loss without fitting an impractical number of models. Typical choices are to use 10% to 20% of the data for testing. Let's reiterate that it is indispensable that we not use the test set at all, not for filtering out rows, not for selecting features, nothing. Now, this presents a new problem because for most machine learning algorithms, we need to select parameters. For example, the number of neighbors k in k nearest neighbors. Here, to follow what you see in books, we will refer to the set of parameters as lambda. Now, we need to optimize algorithm parameters without using our test set, and we know that if we optimize and evaluate on the same data set, we will overtrain. This is where cross-validation is most useful. For each set of algorithm parameters being considered, we want an estimate of the MSE, and then we will choose the parameters that minimize this estimate of the MSE. Cross-validation provides this estimate. First, before we start the cross-validation procedure, it is important to fix all the algorithm parameters. Although we will train the algorithm on the set of training sets, the parameter lambda will be the same across all training sets. We will use yi hat lambda to denote the predictors obtained when we use the parameter lambda. So, if we're going to imitate this definition of MSE, we want to consider datasets that can be thought of as an independent random sample, and we want to do this several times. With k-fold cross-validation, we do it k times. Here, we're showing an example that uses k equals 5. We will eventually end up with k samples, but let's start by describing how we construct the first. We simply pick m equals to n divided by k observations at random. We'll round m if it's not round. And think of these as a random sample. y1b all the way up to ymb, with b equals to 1. This is the first one. We call this the validation set. Now we can fit the model in the training set, then compute the apparent error on the independent set. This is the formula. Note that this is just one sample and will therefore return a noisy estimate of the true error. This is why we take k sample, not just one. In k cross-validation, we randomly split the observations into k non-overlapping sets. Now we repeat the calculation that we just did for each of these sets, b going 1 through k, and we obtain k estimates of the MSE. Then, for our final estimate, we compute the average, given by this formula. And this gives us an estimate of our loss. A final step would be to select the lambda that minimizes the MSE. We have described how to use cross-validation to optimize parameters. However, we now have to take into account the fact that the optimization occurred on the training data, and therefore we need an estimate for our final algorithm based on data that was not used to optimize the choice. Here is where we use the test that we separated early on. We can do cross-validation again if you want, and obtain a final estimate of our expected loss. However, note that this means that our entire compute time gets multiplied by k. You will learn that performing this task takes time because we're performing many complex computations. As a result, we're always looking for ways to reduce this time. Therefore, for the final evaluation, we often just use the one test set. Once we're satisfied with this model and want to make it available to others, we could refit the model on the entire data set without changing the optimization parameters. Now, how do we pick the number of folds k for our cross-validation? Large values of k are preferable because the training data better estimates the original dataset. However, larger values of k will have much slower computation time. For example, 100-fold cross-validation will be 10 times slower than 10-fold cross-validation. For this reason, the choices of k equals 5 or 10 are popular. Now, one way we can improve the variance of our final estimate is to take more samples. One way to do this is to no longer require the training set to be partitioned into known overlapping sets. Instead, we would just pick k sets of some size at random. One popular version of this technique, at each fold, picks observations at random with replacement, which means the same observations can appear twice. This approach has some advantages that we're not going to discuss here, and is generally referred to as the bootstrap. In fact, this is the default approach of the carrot package. We describe how to implement cross-validation with the carrot package in a later video.